Okay, now it's time up. So this is the parallel 11B. My name is Myung-Hoon Park. I'm the convener of this session. The first talk will be by the first talk is about the multi-flavor thermal relic documentor by Johannes. Johannes, are you ready?
Yes, I am. Thank you.
Okay, please start.
Okay, here we go. Good morning. Thank you for the introduction. I'm going to present this work on dark matter production that specifically studies the question, what if dark matter has multiple flavors? The goal of studying dark matter production is to link the one quantity that we know really well about dark matter, its relic abundance, to other observable properties. The issue with dark matter at the moment is that we know really well how much of dark matter there is, and then have lots of constraints on dark matter doing anything else, being too fast, being too charged, and so on, but not much else. So if we now make the hypothesis that this dark matter consists of particles, we want to somehow infer the properties of these particles. And the goal of dark matter production is to link the observed dark matter abundance to particle physics properties that we can observe in the lab or in galaxies or in the universe. So we study production to predict signatures. However, if we're fitting only one number, we'd better keep the model simple, to not overfit things, to not be overly specific, to try to arrive at generic signatures. But if we simplify our models too much, it might be that we miss the relevant phenomenology, so that our model doesn't actually include what in the end may help us find dark matter. This talk is about one such possible complication of the simplest models, which may have different kinds of signatures. We're inspired by the Stern model, which is complicated, right? There's lots of particles in the mass spectrum. We've got a massless photon, there's very light neutrinos, there's leptons, quarks, heavy gauge bosons, the Higgs. And there's relics today of many of these particles. There's relic photons, relic neutrinos, there's relic electrons, there's relic protons, relic neutrons in the form of helium, and so on. And modeling the relic population of the Stern model sector by just one particle would lead you astray. You would never get the universe that we observe today. But for dark matter, in the simplest possibility, we do just that, right? We assume there's one WIMP particle sitting there, it talks to the Stern model, and that's dark matter. There you go. Sometimes the dark matter particle, sometimes we introduce a mediator particle so that the dark matter particle talks to the Stern model via this mediator, which gives you new interesting phenomenology, sometimes makes things easier to see at colliders. But still, that might, of course, not be it. It might be that there's more particles in the dark sector. Maybe there's additional dark matter flavors. So in this talk, that's going to refer to additional dark matter particles with the same gauge quantum numbers as the lightest particle in the dark sector. And the aim of this project is to study what would be the effect of additional dark matter flavors on the relic abundance and then on the signatures that we can hope to see. So to study dark matter flavor, we need some kind of toy model. And we focus on a simple dark matter candidate, Majorana fermion, chargeless, and add a second copy of that. To couple these fermions to the Stern model in a renormalizable way, we need to introduce a mediator. So we do that. That's this charge scalar sigma. And with this mediator, we can then have a term in the Lagrangian that couples via Yukawa coupling the dark matter candidate to some Stern model fermion. And for the purposes of this study, we're interested in dark matter production. So to have the greatest freedom to explore production and not be constrained by the hadronic colliders at the moment, or dark matter direct detection too much, we focus on a leptophilic scenario, coupling only to the right-handed electron. That's a bit ad hoc. It also evades all kinds of standard model flavor constraints, but you could imagine that if we couple to multiple leptons here, the mu and the tau and the electrons, then you get flavor change neutral currents, flavor change, and lots of trouble. But here, for the purposes of studying dark matter production, we focus on this model to have the greatest freedom and really see in the whole parameter space what can happen for dark matter production. So the task is we want to reproduce the observed dark matter abundance, which we can cast in terms of this abundance, which is a small number, right? So that's the dark matter number density normalized to the entropy of the universe, and that's about 10 to the minus 10. And the idea is that we talk about thermal relics, so that this abundance today should be calculable from the connection to a thermal bath, in this case, the standard model thermal bath. And then there's two scenarios which cross over into each other in the middle. Either it can happen that the initial dark matter abundance in the early universe at early times is 0 or negligible, and this increases through interactions with the bath over time until these interactions become rare, and then you end up with the final abundance. That's freezing. Or what can also happen is that the dark matter abundance in the beginning is thermalized with the standard model, so that the abundance is very large, and then it's a question of depletion. How much can we deplete the dark matter before it freezes out, before the connection with the standard model freezes out, and the dark matter abundance stays constant. So in this study, we consider the full range of couplings, both small couplings that lead to freezing and large couplings that lead to freeze out, and anything in between. Now, the standard calculation of thermal relic abundances is with this Boltzmann equation, right? You've got some WIMP candidate, or it can also freeze in particle that evolves over time. It's determined by the dilution, the Hubble dilution term versus the 2-to-2 annihilation process that keeps that ties the number density to its equilibrium value. This is the standard popular Boltzmann equation for single component dark matter that we're all familiar with. Now, if we have a multi-component dark sector, things can look more complicated, right? In principle, any of these species can have its own Boltzmann equation with annihilation terms. They can annihilate with each other, with itself, into standard model particles. And then there's also conversion terms between the dark sector constituents from either scattering or decay. This is very complicated. And often people, even in very complicated dark sectors, like in the SUSY model, where you would have lots of particles that are odd under some stabilizing symmetry, R parity in that case, you don't need to treat this complicated equation, which is very nice. And the reason for that is chemical equilibrium. So that if these conversion reactions are very fast, then you can actually just sum these equations. The individual number densities are related by their equilibrium values, and you end up with a summed Boltzmann equation that look just like the single component one, except that now there is an effective annihilation term here, which includes all of the co-annihilation channels. So this is so there's a best case scenario of if you have additional flavors or additional stuff in your dark sector, and things can get very simple just by chemical equilibrium. If we don't have chemical equilibrium, we need to solve this complicated Boltzmann equation. We cannot use the standard codes like macromegas and so on. So we really need to do that ourselves. So we cast it into some numerics friendly form. And then I need to make sure that this equation isn't stiff, so that if these coefficients here are very large, this gets numerically unstable. But thankfully, in that case, we can just use the chemical equilibrium case again and use the summed equation. So we did that and obtained relic abundances as functions of the Yukawa couplings in this model for some benchmark in the masses. So in this case, the lighter dark matter candidate is 100 GeV, the heavier is 120, and the charge scale sigma is just 430 GeV, which is just the limit from colliders. And what you see is that at very low couplings, we are in the freezing regime, so that the dark matter abundance grows with the couplings. And this is essentially a superposition. It's just a sum of the two dark matter populations. Whereas at very high couplings, we find the standard WIMP regime where psi1 annihilations dominate the determine the relic abundance in the end, so that the relic abundance rises with smaller y1 as expected for WIMP. There's then here the co-annihilation regime if the heavier dark matter candidate is coupled more strongly. And then we get to the fun new things. So it can be that we have a mixture, right? So that one of the particles is coupled feebly. So y1 is very small and y2 is very large. So then one of them behaves as a WIMP and the other one as a fin. But still the final relic abundance is more or less a superposition of the two, sum of the two. There's then also here the well-known mediator co-annihilation region. But in the middle, there's a new regime where chemical equilibrium doesn't hold, but also the processes are not completely decoupled as in freezing. So this is the regime of conversion-driven freeze-out, where conversion reactions between the different dark sector constituents determine the relic abundance, and there is no chemical equilibrium. And interesting things can happen there. But when studying dark matter production, the goal, remember, in the end was to connect the relic abundance to signatures. So we're not done here. We now need to talk about signatures that we can expect from this relic abundance calculation. And there's both general particle physics signatures, which at the moment mostly give constraints, but which could, especially at colliders and searches for the mediator, give lots of specific info on specific models and could be used also then to identify dark matter in the end. But here we're more interested in dark matter specific predictions, in particular how the smarter flavor setup modifies expectations for standard WIMP searches in direct detection and indirect detection, and this additional possibility of decay, that the heavier dark matter component can decay into the lighter one, as well as then the possibility that there is dark matter internal, so to say, signatures, so dark matter being cold, not cold, having long free streaming, things like that. So this now shows the same parameter space in the same plot as before, just showing an overabundance constraint here in orange. And you see that overabundance does a really good job of separating, of carving up parameter space. So there is a viable region in the Friesen region and the viable WIMP region. There's these mixed regions, which are viable from overabundance, but dark matter decay constraints in the early universe do a pretty good job of constraining these. You can also see that here I've chosen a mass benchmark, which is more degenerate in mass. So here the dark matter particles are only split by a few GeV. In this case, co-annihilation becomes more viable and more of the parameter space is open. On the other hand, for example, here new constraints come into play. This is a long-lived charged particle bound from, in this case, if the mass splitting between the dark matter particles is so small, the sigma leaves a anomalous charged track in a detector, and there's limits on that. So here I've chosen a lower value of sigma, which is ruled out if sigma is long-lived enough to leave charged tracks in the detector. So here we can already also see that looking only at dark matter phenomenology, if the second dark matter flavor is much heavier than the lighter one, then it decouples, so to say, from interesting dark matter phenomenology. So here, for example, the co-annihilation region is well in the regime where you would need non-perturbative couplings to get the right relic abundance. Another thing that can happen in the two flavor setup is now we can make one of the two flavors very light, right? So that here, the heavier guy weighs 100 GeV and is the dark matter candidate, whereas the lighter one is just 1 electron volt. And in that case, we can have a dark radiation component, limits on which are shown here. And also the dark matter abundance in the end is determined by how much do I produce of the heavier dark matter flavor, and does it then survive until now? So here are shown the lifetimes of the heavier dark matter flavors, and you can see if it's long-lived enough, if it has the lifetime of CMB decoupling, then it's still measured by the CMB, but it needs to be longer lived than the lifetime of the universe to make up dark matter today. And in this case, here we are in the Friesen regime, but now this there is no overabundance constraint here anymore because dark matter flavor 1 is so very light. And this can lead to interesting dark matter decay signatures. So that here what you see is that depending on the dark matter mass, in this case between hundreds of GeV and MeV, this is the maximum decay signal we can expect at dark matter indirect detection experiments. And you can see that this line here is from Fermilab. Fermilab can see these dark matter decays down to about GeV. And these dashed lines here refer to the case where the lighter dark matter component is actually dark radiation here and not Friesen anymore. And you can get much larger signals, which then could be interesting for future MEV gamma ray observatories like EASTRO or MEGA. Now, the next thing is how our standard WIM search is modified. In the WIM case, we are at large couplings. So Psi2 decays very fast to Psi1, and there's only Psi1 around today, so that all of the signals only depend on Psi1. We can look at direct detection signals, where this leptophilic model is very hard to test, but still it induces a nanopole moment on dark matter, which can be seen in dark matter direct detection experiments. And then, especially in this leptophilic model, there's this thing that the indirect detection signal, the naive one that you would expect annihilation into just leptons, is p-wave suppressed, so that the dominant detection channel would be inverse Bremsstrahlung, would be an internal Bremsstrahlung process, which has a distinct gamma ray spectral feature that would be a very specific sign for this kind of dark matter. So all of these depend on the coupling Y1. So let's see what happens here. And we're back at the degenerate scenario, and you can see that the inverse internal Bremsstrahlung and direct detection bounds don't quite probe the standard WIMP regime here, where the relic abundance is independent of the heavier dark matter flavor. But there happens something interesting when the second dark matter coupling is small. So what happens here is that the second dark matter abundance drops out of chemical equilibrium pretty fast and pretty early, and then stays constant. But there is some conversion going on from Psi2 to Psi1, which still depletes the heavier dark matter and makes the lighter dark matter candidates abundance stay large. And the final abundance in the end is determined by both how fast this conversion is from the initially overabundant Psi2 to Psi1, and how fast annihilations of Psi1 then still are in the end. So in the end, what happens is that you need the coupling Y1 to be larger than you would expect in the naive WIMP case. And this can be interesting for standard WIMP searches, right? So this is it's a zoomed region of this plot, where here we plot as independent parameter the coupling of the lighter dark matter flavor, and here the coupling of the heavier dark matter flavor, and here the coupling of the lighter dark matter flavor, which is a proxy for the direct detection and indirect detection signals. And you can see that in very large couplings, we're in the co-annihilation regime, where traditional WIMP searches are suppressed. But there are these interesting regions where WIMP signals can be boosted, and we get larger signals, which is a hopeful message for future, for example, gamma ray observatories like CTA. Okay, so let me conclude. Here in this work, we studied the possibility of there being multiple dark matter flavors, which is a plausible thing that might be the case. To be concrete, we looked at the leptophilic dark matter with a T-channel mediator, and calculated the relic abundance, where we found that if at least one of the guys is feebly coupled, then you almost get additive yields of the two, which is then quite simple. For large couplings, there's the standard WIMP and co-annihilation scenarios. But for intermediate couplings, there's this non-trivial interplay of annihilation reactions and conversion reactions out of chemical equilibrium, where you can get interesting effects. And this leads then to predictions. One is that we can have this dark matter decay, which would not be possible in a single flavor dark matter scenario, and which can probe Friesen, which is very hard to probe otherwise. And the signal strength in standard WIMP searches can be boosted, which is of interest, of course, to future WIMP experiments. Thank you very much for your attention.
Okay, thank you. It's exactly on time. Do you have any urgent question? If so, please raise your hand. Okay, otherwise that after the last talk, we'll also have a chance to ask the question to him. Okay, so let's move on to the next question, next session, sorry, next talk. Next talk is massive stellar neutrino in the early universe by Leonardo. Please start.
Yes, thanks. But moment, I cannot share the screen.
I can see your screen.
No, it's not my screen.
It's not your screen.
No. Okay, now it's possible. Okay. 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 Hello to all. Thanks for this opportunity and for the presentation. I'm Leonardo Mastrodotaro, and today I will present my work on massive stellar neutrino in the early universe. This work is based on a paper with Pasquale Serpico, Alessandro Mirizzi, and Ninetta Saviano. In this slide, I will do a general introduction to the problem. Then I will talk about the sterile and active neutrino evolution in the early universe. Moreover, I will talk about the temperature evolution. And at the end, I will present the bounds that one can obtain from this treatment about the stellar neutrino parameter space. So the aim of this work is to obtain a precise calculation of the evolution of stellar neutrino in the early universe. And moreover, we want to use the measurements, the precise measurements from BBN and CMB to obtain constraint on the stellar neutrino parameter space. We want to do this because the existence of stellar neutrinos is an interesting possibility of the theoretical physics, because they emerge quite naturally in almost all the beyond standard model theory. So we are interested in to investigate the parameter space, and from BBN and CMB, one can obtain some very precise measurement to do this. Moreover, at the end, we will do also a forecast for the future stage 4 ground-based experiments on the CMB, the so-called CMB S4 experiments, to show how they will constrain the parameter space of the stellar neutrinos. So stellar neutrino emerge quite naturally, enlarging the Pontecorvo matrices, adding a 4 mass eigenstates. The mass of the stellar neutrinos is a free parameter for the model, and in this, for various mass scale, they can solve a lot of the problem of the standard model, like the balloon asymmetry, the dark matter, the instability. Moreover, the other parameters, the free parameters of the model, are the mixing between the stellar neutrinos and the active neutrinos. And in this work, we will take stellar neutrinos that mix only with one active neutrino for time. So we have only two free parameters, the mass of the stellar neutrinos and the mixing with the chosen active neutrino. As said before, we want to obtain a precise calculation of the evolution without approximation. We have chosen a stellar neutrino with a mass under the pion mass. And to do this, we have to solve the Boltzmann equation. In the early universe, it's quite interesting, it's quite useful to introduce two new variables, x and epsilon variable, linked to the scale factor of the universe A and to the momentum of the particle. With these two new variables, the Boltzmann equation is simple as that in the slide, and depend only on x, on the Hubble parameter, and on the integral collision. This problem has already been studied in some references that I show here, and in the first of them, they have done an analytical treatment, while in the other two, they have done a numerical treatment, but focuses only on epsilon p and so on the BBN. We want to show all the CMB also, and so an effect will affect the stellar neutrinos. So the integral collision is that reported in the slides. That is a 9-dimensional collision that depends on the sum of scattering and decay processes for the stellar neutrinos. So to solve this 9-dimensional collision, we have used the Arnstadt procedure. So it's possible to reduce it to a 3-dimensional integral and then to solve it numerically. And this way, we have solved the stellar neutrinos evaluation, so the Boltzmann equation evaluation without approximation for the evolution of the stellar neutrinos. For the active neutrino, we have done the same, but we have introduced also the time average transition probability. In this way, we tracked also the oscillation between active flavor. These are the processes that we have considered for our analysis. These are the main processes for a stellar neutrino under the pion mass, and as it's possible to see, all the processes are only with active neutrino and electrons. So the main particle in our picture are stellar neutrinos, active neutrinos that are tracked with the Boltzmann equation, and electrons and photons that are tracked their evolution with the temperature evolution. A first test for our code is to compare it with the analytical treatment of the Dolgov paper. In that paper, the authors have done an analytical treatment with some approximation, and the first is that the electron mass is taken to 0, and the second is that inside the collisional integral they have taken only Maxwell-Boltzmann distribution instead of Fermi-Dirac distribution. So only to do the test, we have put this approximation into our code, and we have obtained the picture that one can see in the slides, and it's possible to see the perfect agreement in the approximation between our code and the analytical treatment. So this is a quite useful comparison for our code and a benchmark for our code. The other thing that I say to be tracked is the temperature evolution to track the electromagnetic part. And to do this, it's possible to use the energy continuity equation, where ρ is the commoving energy density and P is the commoving pressure. In this way, we have introduced a new variable that is the Z variable that depends on the temperature and on the scale factor of the universe. There are two main situations for the temperature evolution. The first is when the stellar neutrino decouple, and so only active electrons and photons are coupled and so in equilibrium. And the second is also when the active neutrino decouple at a temperature of 5 MeV. In the slide, I have put the couple condition that we used, and it's possible to see also a table with the decoupled temperature for some relevant parameter of the stellar neutrinos. And it's possible to see for the chosen mass, the decoupled temperature is always below the QCD phase transition temperature, and its maximum at 50 MeV temperature. So we have started our code from the QCD phase transition temperature that is 150 MeV, and from that we have started to evolve the stellar neutrino distribution. We have traced their evolution and find their decouple condition. From the decouple, we started to evolve also the temperature, and at 5 MeV, we started to track also the spectral distortion for the active neutrinos. And here it's possible to see some example of results from our code for Z, so for the temperature, and for the commoving energy density of the active neutrinos. So the impact of the stellar neutrinos in the early universe is based on two parameters. The first is the ineffective parameters, that in standard model is 3 with some small correction, while in this case there is a new definition that one can see here, and it starts from a value of 4 and then decrease until a constant value. There are two main situations. The first is for light mass, and in this case is the red curve at 30 MeV, and we observe a smooth decrease of the ineffective and then reaching a constant value. This is because at light mass, stellar neutrinos are always in equilibrium, almost always in equilibrium with the electromagnetic plus, and so they suffer a Boltzmann suppression. While for higher mass, in that case it's the blue curve for 100 MeV, they decouple early, and so they become non-relativistic and their commoving energy density is starting to increase, then they decay and they ineffective reach a constant value. The other parameter that we take into account is the epsilon p parameter that is linked to the primordial helium-4 mass fraction. And to track it, we have used Born estimate calculation in the figure, and it's an approximation way to calculate it that introduces only a systematic error. And to take into account this, we have rescaled our result with the correct value of epsilon p in the standard model. Stellar neutrino affect the epsilon p evolution in two ways: for the spectral distortion of active neutrinos and electrons, and for the changing in the Hubble parameter, where the energy density of the stellar neutrino play a role and change these parameters. So, in this picture, obtain epsilon p and then effective, we have used them to constrain the stellar neutrino parameter space using the Planck value. We have used for the BBN the Planck value of epsilon p, that is 0.245, and for the CMB, we have used likelihood analysis that take into account an effective and epsilon p, as one can see in the system on the slide. All the bounds that I will show are at 2 sigma confidence level. And so these are our results for the evaluation. For light mass, one can see that the bound from the CMB is stronger than the BBN, and so an effective is constrained strongly the parameter space, while for heavier mass, the BBN is stronger, so epsilon p take an important role for the constraint. Moreover, one can see the forecast for the future CMB S4 experiments, and one can see, this experiment will constrain even more the parameter space of stellar neutrinos. Moreover, we have done also a comparison with the present literature, and so the previous results that one can find in literature, and we see how we improve the bounds in the BBN and in the CMB sector, even both cases, but the main result is the improvement in the CMB sector, as one can see in the figure on the left. So finally, in this work, we have done a study of the phenomenology of stellar neutrino with a mass under the pion mass, so under 130 MeV, and we have do a precise calculation of the evolution of these stellar neutrinos without approximation. We have studied the evolution of active neutrinos and temperature that depends on the stellar neutrino that we had in the standard model picture. We have calculated epsilon p and then effective to find some bounds that one can obtain. And finally, we have shown also the forecast of the future CMB S4 experiments. And here I conclude my presentation. Thanks for the attention.
Okay, thank you for giving time. So we have some time for the question. So do you have any questions? If so, please raise your hand. Okay, I think that we don't have any question at this moment. So I think that it's better to move on for the next talk so that we may have some time. Okay, so let's move on to the next talk. Okay, thank you. Next talk is the impact of the operator interference in the dark matter direct detection experiment by Gaurav. Gaurav?
Yeah, thank you.
Okay, so can you start?
Yes, I'm sharing my screen now. Okay. So is it visible, the screen?
Yes, very good.
Okay, yes. Perfect. Okay, thank you very much for this opportunity to talk here in PASCOS. And today I'm going to talk about impact of interference among the operators in dark matter direct detection experiments. And this work I'm doing with my group here in Munich and astroparticle group in Sogang University. Okay. Sorry, I cannot move to the next slide. Okay, so yeah, now it's working. So we have heard a lot of interesting talk about dark matter. So I will be very brief about it when I'm introducing about dark matter. So it is weakly interacting, we know that, and it is non-baryonic, it is mostly cold, and there is no candidate in the standard model of particle physics which satisfy all these properties. Okay, so then how we can detect dark matter? Well, the detection depends what kind of interaction dark matter has with the standard model particles. So it could be produced in LHC or some other collider. We can detect it indirectly, where dark matter could annihilate or decay to the standard model particles, or we can detect it directly, which depend basically when dark matter is coming and hitting a target nuclei, it recoils. And we try to observe this recoil by various methods, maybe through scintillation, through ionization, etc. So this work is focused on direct detection. Okay, so what we do not know about dark matter? So well, we do not know many things. For example, we do not know its mass, what kind of interaction dark matter has with the standard model particles, we do not know. And also we do not know its density and velocity distribution. And that's the reason that there is a lot of uncertainties involved in the calculation or prediction. So when we are talking about direct detection experiment, this is the standard formalism we follow to calculate the rate in an experiment, where the particle physics information goes in the differential cross-section, and velocity distribution and the density here, they basically give rise to astrophysical uncertainties. Like the particle physics uncertainties, they are there in the differential cross-section. And this is of course because of our ignorance about the actual interaction that dark matter could have with the standard model particles. So we have to make some assumptions. For example, we assume that the dark matter is coupling to the standard model particle through spin independent isoscalar interaction. So this is the usually is taken by the most of the experimental collaboration, and they took the coupling of dark matter to proton and neutron to be equal. Second is the velocity distribution. Usually we assume that it is a Maxwellian-Boltzmann distribution and perform our calculation using the density rho chi to be 0.3 in the neighborhood of the sun. All these assumptions we took into account, and finally we arrived to this exclusion plot. And this is the exclusion plot for isoscalar interaction for xenon 1-ton experiment. But this is when you are assuming dark matter coupling to proton and neutron both are equal. And second, there is no interference between this interaction, spin independent interaction, and any other possible interaction. Okay, so this assumption gives us this exclusion plot. What if we include these kind of possibilities? For example, let's relax this assumption that standard spin independent interaction is the only interaction. For example, there are other kind of interaction, and also CP and CN both are not equal, and that gives rise to this exclusion plot. So instead of this blue one, you will have this red one. Okay, there are many models where it is not necessary that both CP and CN to be equal, and second, there is only one kind of interaction. They predict different kind of interactions, but most of the time they compare their parameter space using this blue line, the isoscalar limits, and they think their model is ruled out. But if you consider the interference then this is not the case because your model is still allowed. And that's the reason consideration of the interference is very important. But what happens if again, I'm having some, okay. So what happens if your parameter space lying in this red region? That means your model is ruled out, no matter what. Okay, so this is the important of consideration of interference. So we developed this method, and this is one of the motivation, and we insist that if experimental collaboration could give us, instead of providing this curve for isoscalar, they utilize our methods and provide us this red curve, which is basically including the interference, then it will be the ultimate word. And this will be valid for all kind of models. And that's what I want to insist, that this method is very straightforward, as I will show you, and easy to implement. Okay, so let's generalize the idea. Right now, we are considering that dark matter is only interacting in a spin-independent way to the standard model particles. Let's work in non-relativistic effective field theory, where exists number of interactions depending upon the Galilean invariance. Okay, so here, this is the Hamiltonian density, and this is the idea developed by Hexton et al. What they did, they use this 4 vector and find out that there are 14 kind of interactions possible between dark matter and the standard model particle. Recently, we generalized this idea to arbitrary spin of dark matter. So you can have any spin of dark matter and could perform this kind of analysis. So out of these 14 interactions, many of them interfere with each other. So they affect the results of one interaction or other interaction we will see. Okay, so this in NREFT, basically the differential cross section could be written in terms of amplitude square. This is the standard procedure. And finally, they factorized it in terms of dark matter response function and nuclear response function. And this is very important because they work independently on nuclear response function, and they find out there are 8 possible nuclear response functions if you assume that nuclear ground state is CP even eigenstate. Okay, and just to remind you again, please notice here that Hamiltonian is linear in the coupling. That means the rate is quadratic. And so we can write it in this following form, where R is the matrix and its dimension depends what kind of interaction you are considering. That means, let's say for a spin half particle, I have shown you 14 operators. And for one operator, there are 2 coupling, C0 isoscalar, C1 isovector. So that means R will have dimension of 28 cross 28. And it contains all the information about experiment, basically its resolution, efficiency, exposure, etc. And also dark matter mass, density, and velocity distribution. Everything goes in this R. And now you have this matrices, you compare your rate with some upper bound. Let's say 90% confidence level, whatever you observe, depending upon that. And this is nothing but an ellipse equation. And you find out, okay, this is an ellipse. If you consider your coupling in a 2-dimensional space, this equation will give you an ellipse. If it is more than 2, then it will be, of course, ellipsoid. Okay, so we find out this is for xenon. This is the ellipse. Okay, and as I said before, showing you what is the effect of interference, this slice I'm quoting these response function from Anand et al. Basically, you can see here there are different kind of response function for dark matter. And see, I highlighted there are many interactions which interfere with each other. For example, people usually take C1, which is spin independent interaction. I have shown you this also have interference with other interaction called C3. So that means C1 result should be affected by C3. And this is the important point that we have considered. Okay, so this is the method first developed by Brenner, Ibarra, Rappelt in our group here, and they did this analysis for ice cube. And now we generalize this idea to dark matter direct detection and for different kind of experiments. So what is their idea simply? Let's see, in 2 dimensions, we have achieved this ellipse here. And now suppose you are having isoscalar scenario. That means the maximum coupling that you could have will where this ellipse will cut the axis. But if you are having interference between the operators, then the actual value of C is not this, but here. Okay, so how to get this value of C maximum? So, well, they construct this Lagrangian where lambda is a Lagrange multiplier, and then doing some optimization, we find out finally what is the value of C max is this simple formula. So what an experiment collaboration has to do, just they have to utilize this formula and give us the limits, which is like the ultimate word for the exclusion limits, independent of the model. Every model could test their output against those exclusion plot. Okay, I just want to make this comment here. This R matrices we calculated using our code WIMPDD. We released it just 3 days back, and Songyun Kang has given talk about it. He talked about it yesterday. Okay, so this is I already talked about. Okay. And now we generalize this method for more than one experiment for direct detection. And you could see instead of one, now you have 2 ellipses. One is correspond to xenon, another is correspond to pico. And you could see here, now the allowed value is even more constraining. Before it was here, but now you are considering other experiment also. So the allowed value of C is somewhat more constraining, it will be here. Okay, and this is the Lagrangian when you are considering more than one experiment. And again, we follow similar procedure and find out what is the value of C here, C max here. Just one important point I want to make here, that there is only one Lagrange multiplier is involved in the calculation. That means you could generalize these methods to n number of experiments without any complication. So this is very powerful and very straightforward to implement. Okay, I could skip this. This is just technical detail about this method. And I could show you these ellipses that we have obtained for 2 experiments, xenon and pico. And why it is important to consider 2 experiments, you could see here. For example, this C1 is a spin independent interaction. That's what we usually consider in our calculations. And you see here, xenon is the most constraining experiment. So of course, there is no constraint from pico. Always this is xenon, which is dominating. But if you go to spin dependent interaction like C4, C7, C6, you could see that xenon and pico are, let's say, orthogonal to each other. So that means they cover the direction very different to each other. And that's why target complementarity is important. And that is one of the reasons we consider more than one experiment in our calculation. Okay, here is some of the results, just to give you an idea. You see, this is the C1, that means standard spin independent interaction. And usually we take isoscalar interaction, that means this dot line for xenon. But now if you consider interferences between different operators, what we achieve is the solid line. And you see the relaxation of the limits by 2 orders of magnitude. And that's very important. Similar, the other kind of interaction like C12, here I say C12 because this is coming from operator O12. The list I have already shown you. And this interfered with other interaction like C11 and C15. And here also you will see the relaxation around 2 orders of magnitude. And then question is arising that this point is allowed or not. And now again, it depends. If in your model you are having more than one coupling and they are interfering, or you are having in your model dark matter coupling to CP and CN are different, then this is not the right way to compare your limit with this most stringent bound from isoscalar. Same story goes for other interaction, just to give you some idea about spin dependent interaction. Here I have shown C4 and C6, and here the bound is relaxed by 3 order of magnitude. And this is the result when you combine experiments. And here you could see that this combined experiment is more constraining. I have not shown you the other line from Xenon. It should be somewhere here up, and PASCOS should be somewhere more up. Anyway, so this is the overall idea of including interference in our calculation. Okay, so with this, I could summarize that consideration of single coupling leads to very stringent bound. Interference is a very important effect one should take into account. And we developed, basically we extended this method developed by Brenner et al. To direct detection experiments. And we generalized it to more than one experiment because of complementarity between different targets, as I have shown you through different kind of ellipses. And we find out that this bound is relaxed by 2 to 3 order of magnitude, depending upon the interaction. And the important message is that when model builder are comparing their results against these exclusion plots, they should be very careful. If their model is having more than one interaction, then this is not, they are comparing something like very stringent bound. They are comparing their model against very stringent bound. And again, this is very useful for the model builder. And I insist again that if experimental collaboration could utilize our method and give us exclusion plot, which is I have shown you including the interferences, then it will be like ultimate word, and it will be true for all of the models. With this, thank you very much for your attention.
Okay, thank you for the nice talk. We have actually 8 minutes, but yeah, so do you have questions or some comment? Actually, I have some questions. So you treat this all of these EPT operators, they are independent, right? Independently, but can you get this combine to compare the result, and you put this to allow the interference between the independent operators, right?
Yes, yes, exactly. Yeah. So they are independent, but they interfere with each other.
Yeah, but in reality, when you have some interaction between the fundamental particle and the dark matter, and then you go to going down to this directed okay, for the interaction and going down to this EPT operator, then some of the EPT operator, they are correlated with each other, right?
Yes, that's true. Exactly. This is the case because some of the relativistic, let's say, if you take an example for anapole operator, anapole dark matter, and you go to its non-relativistic limit, then it is the combination of operator O8 and O9. Okay.
Yes.
And you can see here O8 and O9 interfere with each other. So that's why it is important to consider this effect. Yes. I guess that's what you are asking, right?
Kind of. Okay, but for the result, and for the result, then you have this dark matter and this one coupling and show the this bound. Then you maximize the other coupling to show the difference to allow the region.
Yes.
Just like
okay. Oh, here?
Yes. Yeah. Yeah. For example, not this one. For example, the expression.
Okay,
yes, this one. Yes. Yes. So 2 order of magnitude, the C1, and then you move the C3 for the allowed region.
Yes, exactly. That's true.
This is maximum.
Yes, maximum of C3. Yeah, exactly. That's true. That's true.
Oh, there's a question. Okay, Johannes, please ask a question.
Hello. My question is, can you use this for your target optimization? So what kind of targets would be interesting?
Target optimization, I guess this you could see here, Like if you take the interaction, it depends what kind of interaction you are taking into account. For example, you are taking standard interaction, spin independent, which is coherent. Then of course, xenon will be important, as you can see here, because this is the most constraining, right? And here, of course, because they are orthogonal to each other, both are important. So in this way, you could test the complementarity. But for target optimization, I guess that's what you are asking exactly, isn't it? Yeah.
Yeah.
So in this way, you could check which target is important and which is not important. Yeah.
Okay, thanks.
Okay, so now do you have another question? Yeah, if not, we can move on the next talk. Okay, thank you. So the final talk of this session will be given by Rajiv about the quantum fluctuation of energy in hot relativistic gas of fermions. Okay, please start.
Yeah, can you see the slides?
Yes, I can see clearly.
Okay. So thank you very much for the platform, and thank you to all the speakers. Excellent talks. I've been watching almost everything on the YouTube. So yeah. So my topic a bit of the particle physics. This is related to relativistic heavy ion collisions. And this talk is actually focused on one of the important fundamental questions which we have in the relativistic heavy ion collisions. So I'll just give a brief overview. So I'm a PhD student, and these two are my supervisors, and he is my colleague in our group. And the details of this talk will be available in this paper. So I'll be speaking about the fluctuations which are happening and which can be calculated for the spin half particles. So before going to details, I'll just give you the brief motivation that why we are doing this. This is a schematic picture of the relativistic heavy ion collisions, and you can see here that means QGP is found to be the most vertical and most hawkish fluid ever produced in the laboratory. But to understand the evolution of QGP, relativistic hydrodynamics has been widely accepted effective theory to describe this QGP evolution. And means for the QGP evolution, means to study QGP evolution, we have to use the perfect fluid hydrodynamics. Means most of the people study the perfect fluid hydrodynamics, and some people in some community people are studying the dissipative or viscosity corrections to this perfect fluid hydrodynamics to get more precise values. But the most important point here is that to study the evolution of QGP, we need to use some local equilibrium means hypothesis. Means to study the evolution of QGP, we need to define some fluid element for the study of this QGP, and for that fluid element, we have some like energy density, pressure. Means every fluid element in this QGP small system, we have local thermodynamics, and that has to be satisfied for each of the fluid element to apply the relativistic hydrodynamics. Otherwise, we will not be able to understand, or we will not be able to study the QGP. The point is that every fluid element have T mu, that is energy momentum tensor, which gives us the information about the energy density and pressure locally in the local equilibrium. But there can be various forms of T mu, energy momentum tensor, for defined specifically for the fluid element. And people in the heavy ion community are studying these various forms of energy momentum tensor, but none of the energy momentum tensor has been able to describe the data. Means none of the theory using different form of energy momentum tensor has been able to describe completely the data. So our goal is to understand that which key mu energy momentum tensor is actually fundamental or better than the other by understanding the fluctuations of energy momentum tensor. So fluctuations of various physical quantities play a very important role in all of physics, in possibly phase transitions, the early universe, and large-scale structure of the universe, dissipative phenomena, and these fluctuations actually comes from the quantum asymptotic relation and or the thermodynamical systems. And this I was speaking about the evolution of the QGP can be very well described by the relativistic dissipative hydrodynamics. And one of the key concepts used in this study is the concept of energy density and pressure. And I was telling that the fluid element has to be defined to get the numerical simulations of relativistic hydrodynamics. But the fluid element has almost zero size. It's not zero size, but we assume to be almost zero size. I mean the size of the fluid element, which has to be introduced in the relativistic hydrodynamic theory, has to be smaller than the system, the macroscopic system, but has to be larger than the particle size. Therefore, you can consider that each fluid element have number of particles inside. Okay. And the Hydra models we use to conclude that the energy density in this collision process have large values. Yeah, so to define or to construct or to calculate the quantum fluctuations of the energy density for spin-half particles, I need to have this field operator, which many of you, I think, know. And these are the spinors, and these are, and A and B are the creation and annihilation operators, where omega k is the energy of the particle, with k being the momentum. Okay, so to calculate the inner quantum fluctuation, I need to have the expectation values of the creation and annihilation operators, which we use. So these are the formulas actually. So these are the formulas for the A, and we can have similar formulas for the B's, which is this for the antiparticles, so to speak. And F is Fermi-Dirac distribution function for particles. Similarly, F bar will be the Fermi-Dirac distribution function for antiparticles. Okay, yeah. So before going to calculate, we need to define the energy density operator. So this is the energy density operator, and this is the time component or the key component of the key mu energy momentum tensor. So we use the Gaussian profile to define the subsystem is small sa inside the bigger system. You can consider that the bigger system is QGP is the QGP, and the smaller system is actually the fluid element. So this we define this energy density operator for the smaller subsystem using a Gaussian profile. Why? Because if we do not use the Gaussian profile and if we use some other profile, for example, cube, then there might be possibility of having a sharp boundary effects. So to neglect or to ignore that the boundary effects of the cubical profile, we have to use the Gaussian profile so that we don't have these effects. And these are the formulas for to calculate the fluctuation, where sigma square is expectation value of this, means T0 minus T0 square, and this is the normalized standard deviation. One important information is here that to calculate this sigma n, we can have, there is two types, or there are two formulas in the literature. One is that, which is here, and the other is this numerator divided by this first value, not the second term, but the first term. So and we have checked that both the formulas give the same expression for the fluctuations. Okay. Yeah. So for any means we know that from the quantum field theory or quantum mechanics that for any continuous symmetry there is a conserved current, means from the Noether theorem, right? And this is the conservation of K mu. But to use the perfect fluid hydrodynamics in the relativistic heavy-ion collision, we need to have K mu which is symmetric in mu nu, right? And therefore, like we have a K mu from the Dirac-Lagrangian, which is canonical energy momentum tensor, and that canonical energy momentum tensor is actually antisymmetric. Okay, so to use the K mu to use K mu in the relativistic hydrodynamics or the perfect fluid hydrodynamics, we have to symmetrize the K mu, and that is done by one of the ways that is called pseudo-gauge transformation. So suppose that this is canonical K mu, and this is the pseudo-gauge transformation which we add or subtract to this canonical K mu, and then we get symmetrized K mu, which we can use in the relativistic hydrodynamical simulations. So our goal here is that there are various forms of pseudo-gauge transformation, and because of that, we can have various forms of symmetric K mu. So which K mu is actually better or not, or none of them is actually fundamental enough to comment on that. We will do the calculation to get the answer for this question. So we aim here to study the dependence of these quantum fluctuations on this pseudo-gauge transformation. I think if you have any question, please just interrupt. Okay. So this is a canonical energy momentum tensor which I was talking from the Dirac-Lagrangian, which is antisymmetric in mu nu, and these are the three forms of other K mu, which is this P prime K mu, by adding the pseudo-gauge transformation. What is the form of pseudo-gauge transformation? I am not commenting now, but you can have a look on the paper in the paper which I mentioned before. But the total P prime K mu for the three different pseudo-gauges is here. So in this I have taken this three particular choice because in the heavy-ion physics, these three are actually being used very much because because we also have the spin polarization, and that is very much related. Means that is very much important to understand the spin polarization of lambda hyperons, but that is a different story. But here we are just focusing on these three forms of energy momentum tensor. So this is a Bellefante form of Rosenfeld form of the energy momentum tensor. This is GLW, and this is the Hilge-Ward and Wyckoff form of K mu. Okay. So now I'll do the calculation for T00 of each of the energy momentum tensor and find the fluctuation expression for each of them. So interestingly, that for each of the K mu, we have found that the energy density, the average value of the energy momentum tensor is actually the same for each of them. Doesn't matter what is the pseudo-gauge here, but for each of the K mu, the thermal expectation value is actually same, which I can show you here. But the fluctuation expression for each of them is different. I have not specified the form of the expression because that is more complicated and very big. So I don't want to scare the people. But the point here is that because of the different pseudo-gauges, we have the different quantum fluctuation expression for each of the T00 component. Okay. So now I'll go to the numerical simulations and numerical plots where we compare the fluctuation expression for each of them and for different values of mass and temperature. Okay. So here you will see that we are comparing this with the different form of T mu, different form of the T00 component for different mass, and temperature is fixed, and G is actually the degeneracy. Okay, here the degeneracy is 10 and the temperature is around 0.15 GeV. Here you will see that for larger mass, for example 1 GeV, the quantum fluctuation is actually high, and for smaller mass the quantum fluctuation is small. Means the magnitude is quite small than the larger mass. So the point here is that the quantum fluctuation actually depends on the m/t ratio. Okay, so if the m/t ratio is larger than 1, then we found that quantum fluctuations are large, and if the m/t ratio is less than 1, then we found that the quantum fluctuation the magnitude is quite smaller. And here is the plot for the particular value of m, particular value of t, and g is 10. This plot is actually shown to understand that what will happen to the quantum fluctuations if the mass of the particle is very small. So this is here, and especially for the canonical T mu or the BR, the Bellefonte-Rosenfeld T mu, this is the quantum fluctuation actually drops to very negligible value. One more point here is that you can see that here the mass over temperature ratio is quite small. That means much smaller, and this greatly affects this part of the energy momentum tensor, which is T mu canonical. The other plot which I'm going to see that to explain, like one can argue, one can question that the expression which you found for the quantum fluctuation, how do you know that that is correct? One of the check is that if you go to the large system size where the A is very larger than 1 Fermi or around 1 Fermi, then we reproduce the classical limit of the fluctuations of the energy momentum tensor or the energy density. In that case, all the three quantum fluctuation expression goes to 1. It means that we reproduce classical limit when we increase the system size. So that is one of the check which we have done, and we found out that yes, all the three P mu regardless of the Segal gauge, all of them converge to a classical limit if we increase the system size. Okay, and this is again for this another set of parameters m/t. Here m/t is 1, and here m/t is larger than 1. Again, you can see that for m/t equal to 1, this T mu canonical is actually very much smaller than the other Segal gauges, other Segal gauge conformations. You can ask that why this A is starting from 0.4, because for the very small system size, for example, going like system size going from below than 0.4, the fluctuation diverges. So this is actually the coarse graining thing, which can be useful for the heavy ion experiments. That we can means the fluid element size has to be large enough not to include the fluctuation, but if we define the fluid element size is small enough, like for example less than 0.4 Fermi, then we have to include the quantum fluctuations in the numerical simulations of relativistic hydrodynamics. Otherwise, the precision or the agreement between the theoretical models and the experimental data will not happen to particular accuracy. So this framework of these calculations also specifies that to which fluid element size we can ignore the quantum fluctuations or we can include the quantum fluctuations. And the second point is here is that if we calculate or if we include the quantum fluctuations, then that information that does not give information that which of the energy momentum is actually better or fundamental. So to explain the data, we have to have means to explain the system behavior, we have to choose a particular sugar gauge, and then we can calculate or do, and then we can numerically simulate and compare with the data. But for large system size, no, doesn't matter what your sugar gauge transformation is, but yes, all of them converge to a classical limit. Thank you.
Okay, so now it's time for the question. Do you have a question? Okay, so I don't see any question here. So yeah, because you have already explained many things during your talk. So this is the end of this session. So after break, then we'll have the plenary 8. Okay, so thank you for attending this session. And by the way, if you have some question for another speaker, then you can raise your hand. Otherwise, then we end up this session. Okay, this is the end of the session, parallel 11B. Thank you, and see you later soon.